Hello, in this video I'm going to go into more detail on using background tiles and their attributes in gbdk. So to start with, I will show you the program running that. So here we go. These are various 16 by 16 pixel images split into 2 by 2 tiles here, and we've got a load of them moving around the screen here. So this demo will show you how to play around with characters from background tiles, and one of the important things on this as well is getting to grips with the color attribute table. So you'll notice on some of these, when they come near each other, the colors kind of clash, and that's because the attribute table is obviously not as fine as the tile map. So as a result, when similar characters come near each other, the palette of one is used for the other. So one way you can get around that is to design levels using 16 by 16 images or 2 by 2 tiles. That way everything kind of aligns correctly on the attribute maps and will alleviate the color attribute problem. Another thing to note when it comes to the NES with gbdk is there's a limit of how many tiles you can draw whilst the screen is still on. The reason for that is gbdk is recording the locations of those tiles into a list, which when the console goes into vertical blank, that list is then copied to the VRAM. But due to the limits of the amount of RAM on the NES, only 32 tiles can be copied whilst the display is on. So as you can see here, there appears to be more than that actually moving around at a time. And the way you get around that is you update small groups of tiles at any one update. So all of these I'm only moving one block of 4 tiles each update, but it gives the illusion that they're all kind of moving at once due to the speed at which the update occurs. So also in the code here as well, I've included a font set and some font printing methods. So be aware, if you call the printing of text whilst you're moving a large group of characters around, then those tiles also count. So one way to get around loads of these limits are to draw your levels first while the display is off. Draw as much as you can, and then once you've got everything positioned how you want it, then turn the display on, and then you only would want to draw tiles as and when you kind of need to. If you have to draw a load of them, for example, if you imagine Space Invaders with all of those the aliens moving as a group, well, you would just move one of those at a time in that group. As is the case here, you would you kind of have to count the updates to the program, and then only copy a certain amount of tiles during that one update. So there are all 4 palettes are in use here for the background tiles. I will close this and I will jump into some graphics here to show you what we've got. So this is the tiles for this demo here. You can see we've got a font set here of the uppercase characters. When designing a font set, I would always kind of try and keep the numbers and letters to start from tile, I think this is 48 in this case. These correspond to the ASCII key values. Although ASCII was not obviously used on these older consoles, using printing commands, it kind of makes sense to kind of put the characters where you would expect them to be in a font set. So I usually keep tile 32 clear because that's usually where the space character would be. When you press the space bar, there is actually a graphic associated with that, usually on older computers and when using bitmap fonts. And then tile 0 has a special use case on all of the tile-based consoles as well. Tile 0 is usually what's displayed as the default sort of background everywhere on a tile map. So if you've got no values in the tile map in memory, then tile 0 is what's actually drawn to the screen. It's not a blank, it needs to be an actual graphic somewhere. And as you can see here, these are the parts of the larger images. So these are 16 by 16 pixel images, and as you can see here, I first draw the tiles going across and then draw them going down. Now the colours here are as if I was creating the graphics for the Game Boy here. That's because I've used my Game Boy graphics converter for getting the tile data here. gbdk allows us to use the Game Boy format. So as I already have a graphics converter for that, it makes sense to use that rather than the native tile data format for the NES. The only thing that we can't use when we convert this are the palettes here. So when you create the sort of colors here, it's always best to kind of have the NES color palette on hand so that you can kind of match the colors as best as you can. So you can see them all here, like so these colors I've used for these characters here are kind of closely matching one of these values here. And then once you've converted it, so if you've not seen the videos before on the Game Boy graphics converter, I recommend you have a look for that here and get familiar with that. I'll show you the program here, what I have. So I've got two versions of it. There's a Windows version and a Linux version. On my site I have the source code for the Linux version uploaded there, so you could probably build that for Mac. So if we go in here, and then you'll see here the exact same image again of all the tiles, and then this is the data for them here. So these color palettes are not used, but the tile data here, which outputs, is obviously what we need here. So notice here it tells you how many tiles are there, and it also gives you a palette count as well, although obviously this is not needed here. And then with the data there, now if I open this up in code blocks here, recommend you go back and see how I installed code blocks on Windows and Linux if you've not done so already, unless of course you are familiar with a different program for coding on, like. So when it comes to the palettes, you might have to sort of like play around with trying to match up the colors in the palette here. So just have a look through what kind of looks closest. So although 21 here in hex looks closer to that, I decided to go with a slightly darker value after actually viewing it. So color wise, you might have to tweak these to see what looks best on the console when it actually runs, because although this is what we see here in this palette, it probably looks different on the actual console. And for me as well, I've got two monitors. So I've got one which is slightly duller, which is the monitor here, and then my other monitor, the other side, is brighter. So it there's kind of conflicts there depending on which one you design the graphics on. And then so we've got the white here. So we've got the blue, we've got the white, and then the black here. I've chose 15 here. So that's pretty much that whole palette there. Oh yeah, and 2C here for the cyan sort of color, and then the other palette here for the pink. Now these display differently in the emulator I'm using, Messen, which I would recommend using. When I drew the characters, I initially went with some of these brighter colours here, but they are very sort of bright on the actual console itself, or rather the emulator I'm using. I've no idea what it actually looks like on the NES. If you've got one, then you run this on, let me know. I would be interested to see whether the colours are actually accurate, which I've been using here. So I've gone with this colour here for the pink colour here, and then the red I've gone for 6, and then 15 for black again. So the first palette here, this first colour here is the background colour, and then this first colour here on the other 3 palettes is kind of not used at all really. That is transparent. So make your palettes out and then run the program, and obviously you'll probably have to tweak it from there to get things to how you want them to look. So what I'll go over now is I'll go over some of the functions which are in here for creating this. So one of the first things I'll mention is the makefile here. So when you install gbdk, obviously make sure you make a note of where it's actually installed. And then if you were to design your own programs from scratch, I would recommend using the base project for the Game Boy, which I showed in the first video of installing gbdk as a template for everything. So if I open that up and then show you what that kind of looks like. So if I move this across here, open that in the text editor. So this is what the program looks like on there. So to use this on the NES, all you would need to do is to select the appropriate header file for the NES. And then you would have to amend the makefile from here. So this is the Game Boy one. So to convert this to using the NES, you would just add that line there after here. So you would press tab after there, and then you would paste that line into there, and then change the binary name here to .nes, not .gb, and then you can tweak some of these things here to remove .gb. That's obviously not needed. ADB, I don't believe that's needed either. And then that would be good to build for the NES then. And you can find where I got the this stuff from by going to where you installed gbdk. And in the examples folder there, if you go into the NES folder, and then if you open this up in a text editor to have a look at it, you'll see it's got this line here. So this differs slightly from what I've got here, but it basically has most of the same sort of stuff here, just arranged slightly differently. So this is specific for the NES here. Now I will get back to what's in the code here. So I've called the characters actors, and I've got some structures here to hold some information about them. So in the utilities modules and headers here, I've got some type defs here, so we can use U8 for unsigned chars and U16 for unsigned shorts. These constants here define the width of the screen and the height of the screen and tiles. This is a simple structure for a countdown timer, or any sort of timer really. We update these timers once per game loop, so they can just automatically be on countdown. So when you initialize these, you bung the start time, which gets put into this value. The countdown copies the timer value, and then every time you update the timer, the countdown is subtracted by 1. When the countdown timer goes less than 0, so it loops round to 255, then we set this to true, and then you know that your timer is elapsed. And these are some this one here isn't even needed on here, but this is a carryover from the Game Boy. We obviously don't have unsigned shorts for our palette bytes here. These are just some variables to work with our actors here, and this is a structure to hold all of our actors. So we've got the horizontal position of them, vertical position. Notice that each of these is actually an array, so it allows us to kind of easily group everything together in a workable area. And this variable here defines the maximum amount of them. So we've got the horizontal, vertical position there. The tile start is, if you look back on here, you'll see that there's actually 2 frames. So this is one frame of our fish, and then this is the next frame. So to start with, we record the start tile where the graphic is. So for the fish, the start tile is this one here, and then it allows us, when we change a frame number, we don't need to refer to the tile specifically. We can just have the frame times 4 and then add that to the starting tile, and that gives us the offset of the next frame, because each image is composed of 4 tiles. And then we've got the what direction the character is facing, which would be one or more of these variables here. So these are using bit flags, so we can combine these together. So we could, in theory, move diagonally and record that in the face and value of each actor. Although loads of this is probably overkill really for actors made of tiles, but you could still have all of this. And then we've got movement types here. So the actors, there are 2 different types of movement types for them. One of the sets of actors only moves up and down, and the other only moves left and right. So we can specify that in our movement type here. And then the animation type, I'll put 2 for this. The animation types here, we've got, all of them are kind of loops. I've not got any static actors on display here, but you could have that. And then it says palette ID here. That's the value you would put into the attribute table to say what palette to use for our tiles. And then this holds the count, how many of them are actually there. So this is the maximum amount of actors that can be in this array. The reason why I've put it up here is so you can change it as and when you need. It could be 50, it could be more. One thing to bear in mind is obviously these all take up a lot of memory, and there is a limit to the amount of RAM that we have on the Game Boy, so that's something to bear in mind as well. Although the reality is that the bigger the actors are in tiles, the less of them you will probably have anyway, so probably not too much of an issue really. And then the frame ID, this one obviously is not an array either, so the frame ID kind of works on all of the group. All of the characters only have 2 frames anyway, so the frame ID will either be 0 or 1, and that will then apply to all of the actors when they're drawn. These are the functions to work on our tick timers. We initialize them by passing them as a reference. So to start with, in the initialize, we put in the delay that we want. Then all we do each time is we call the update timer with our timers variables all set, and then when the timer reaches 0, it will return true, and then you would need to reset the timer. And then these commands here load our tiles into VRAM to work with, and this command here loads our palettes in as well. This command will clear the screen, so I would recommend only sort of doing this at the start of the program or start of a level or something like that while the display is off. And then this command here will draw 1 tile, and then this will draw a set of 2x2 tiles. So I have left these in because this whole program here is literally a copy of the Game Boy version that I've done. The whole reason to do things in this manner is all the programs I intend to write will all have very similar functions, if you like. So what that means is in the future you could be running this exact program maybe on the Game Boy Advanced or maybe the Nintendo DS, and the functions will be exactly the same here as they will be there. So I intend to I try to keep a consistent lot of functions. So some of these others here, so this one thing to bear in mind when using the random function on the NES is because of the limited amount of memory, there's no modular operator. So the mod symbol, for those who aren't aware, is literally just a percentage sign. So what that does is that limits the number using that symbol to 0 and the maximum amount of that number. It kind of confines the number within a range, if you like, but we don't have options to use that operator on the NES. So the best way to use the rand function when you use it is to pass a bit mask. So for example, if you were wanting a random number for somewhere like on the screen's width, for example, so between 0 and if you wanted a random number between 0 and 31, then obviously the maximum number would be 32. But because we don't have the mod operator, you would literally just pass in 31. The reason for that is if you look in binary at that, 31 works nicely as a bit mask. So that means whatever number is returned from the rand function, which would always be a number between 0 and 255, we would then apply our bit mask to that, and then that would keep it within a set range. Hopefully that kind of makes some sense to you. You kind of will probably have to look into that more yourself in the future to see what numbers are kind of returned for that. So this command here initializes the random value. On most of these old consoles, the way you kind of want to do that to keep it simple is when you have like a title screen or something like that, and you're literally just waiting for the player to press start, you constantly update a value in the background, and then when the player presses start, you then use that value to seed the random number generator, which is a nice way to do that on these consoles. And then this command here will clear like a strip going across the screen of tiles to 0. This will clear a vertical strip to 0, and this will output a load of tiles to form a string of tiles, if you like. So you can print like messages to the screen using this. So it's not printf. This is a custom print command, and that summarizes the utilities function names. The actual code for them themselves are in here, so it's recommended to have a look at some of these. Most of it is very sort of simple stuff really when it comes to it. For example, when you initialize the tick timer here, it gets passed through, you set the elapse to false, and then put the delay into the countdown and the timer value, and then that's ready to run. When you call update, it will only change the values in there if the timer hasn't elapsed, and then it returns the state of the timer elapsed. So these are just some useful functions to work with common data types. And then these use the normal gbdk specific commands here. So if you look in these functions here, you'll see the gbdk specific things which are sort of wrapped by these functions. Now this one here, which draws a 2x2 tile here, so you're in the tile put, it's not actually touching the attribute bytes at all, so no color changes are taking place there. It's only writing a byte to the name table, which is the tile map. Whereas in the 2x2 one here, oh yeah, I didn't actually, this is an important thing in here which I put. So this variable here, so these are global variables which are for you to access anywhere, which is a recommended route to take when working with these old consoles with limited memory, or rather the 8-bit consoles, should I say. So this tile attribute variable here, this is you should only put a number between 0 and 3 in this. This is for basically setting the palette ID when you call this command here. So the first couple of parts here will write 4 bytes into the tile map. So we use this command here as it allows us to write bytes faster. What this command does is it actually gets the address and VRAM from the actual tile map, so we don't have to keep first getting the location in the tile map where we want to draw to. Get the tile, get the address, load it into our pointer here, and then you literally just write 1 byte using this command here. So then what we have to do then is update the byte, because we're drawing 2x2 tiles. So to draw our fish here, we have to write 4 bytes to draw 1 frame of the 2x2 image. So first off, we draw the top here, and then we need to add 31 to get back beneath it to the row below. Then once we've drawn all of that, we then use the set background attribute command with the tile attribute byte, and then we basically plot the palette location for each of those 4 tiles. I chose to use this command as the tiles move only 1 tile at a time, and the tile attribute map is obviously in blocks of 16, as in 2x2 tiles at a time. There's obviously a chance that we could miss out on a proper sort of location, so I used their commands for doing that there. The print command uses similar sort of stuff to this here, really, except what we're working with here is, once we get the location where we want to print to in the tile map, we then repurpose one of these passed in variables to read, or rather be a holder for one of the bytes from the message here. Then we loop through all of the characters in here as long as the value is greater than 0, 0 being what's used to be the end line in a string. Then we draw that tile to the screen, and then we also plot the colour using the tile attribute byte, which you should set before calling this. And then these are the rand statements here. So this calls the gbdk init rand function with the lseed value, which is a global attribute that I created and pretty much use in all of the 8-bit machines and 16-bit ones as well, as the init rand function takes a 16-bit number to seed it, and then the rand function itself uses the max value here as a mask to the bytes returned by rand, and then returns that. And our 2 clear strip commands just loop through areas. So this just does a horizontal strip here using the width value. This does a vertical strip here. So when using these, obviously need to be careful how many tiles you're actually drawing while the screen is on. So if we jump into the main code now, not sure what I altered there, so best not save that. So we started up, this holds the starting positions here, and this is the maximum positions on the screen, horizontal and vertical, that our actors can move. Here's using that actor group structure here to hold our actors, and then we have a boolean here to say whether our actors have actually moved or not. So I'll first, before I go to the individual bits here, jump down to the main bit itself. So this is the main loop in the program here. So to start off with, we always should start with the NES with the display off. I'm pretty sure gbdk does that anyway, but just in case, we will do that here. So I probably didn't really need to call that just there, to be honest, so I'll leave that there anyway. It's not really that important. I'm not really using random actually much in here. This is a carryover from one of the other programs. So first off, while the display is off, we set our tiles here. So you can use this while the display is on, but obviously you need to be mindful how many bytes you try and write. There is a bit in the gbdk documentation which is very useful here in the manual. So there's a specific bit here which is definitely worth checking out. I'll see if I can find it a minute. It's got guidelines on coding for the NES. So this bit here is definitely worth checking out here. This is it basically goes over some of the key sort of differences, but there is a key bit here on the NES which goes into some key limitations, and it explains about the limits of how many tiles you can draw while the screen is on, and then it recommends that you draw no more, well, it says you shouldn't draw any more than 32 for the NES anyway. Yeah, here we go, this bit here. So this lays down a load of key things here that gbdk does in the background for you, and how to work nicely with this. I won't go into any more of that here, otherwise my video will be going on for hours. So this command here loads our oh yeah, I didn't get to that. I'll get to this now. So I always use this header file here to detail out where all of the key tiles are that I want to work with, so it allows accessing them later on, makes it nice and easy to work with. So you'll see here that I've got the UDG wall. So that's where the tile, these are just nice names to work with the tiles. And then the heart character here, which is 64. And then that says where the frames are there. So fish here, frame 1 is at tile 2. And then, like I said, all of the 16 by 16 pixel images use 4 tiles. So we can just add 4 on to the previous definition there, and then so on and so forth. So these are just nice references to work with the graphics here. And then in here as well, these here, this is an abbreviation for graphic tile start. So our font set starts at tile 0, and we have 112 of those tiles. If we were adding more graphics to different parts, we would add more graphic tile start and graphic tile count components which build upon these here. So we don't need to remember offhand where all these things are. We can literally just create constant variables to do all of that for us. In here I always reference where the data actually stored. So in this case, you'll see this is where the arrays are defined, and this is where they're implemented here. We've got tiles. Well, this one obviously isn't implemented anywhere, so I can delete that. So we've got the color tiles and the palettes there. And then this was just an animation delay here. Again, it's a carryover from the Game Boy one. Always make sure when working with the NES that you have the correct header files in there. So while the display is off, we load our tiles into memory there, and then clear the screen while the display is off. We initialize our actors while the display is off, so that we draw them all in place at the beginning. Then wait for the vertical blank. Just double check what I've put in here. So this sets them all up. See, we're using the screen height there. Our first load of actors. So you can pretty much, because of the way that this structure has been made out, you could pretty much plug loads of different things into how these sort of actors move. But in the case here, start off with, we draw the strips of tiles going down the screen vertically. So we move in steps of 2, because obviously they're 2 tiles high. Loads of this is kind of self-explanatory here. This is the initializing the vertical actors here. You'll see we set the start frames for them, and then use the palettes there. So you might have to refer to the image again to. So you see here the bat. If we set some of these local variables here to help us define these. So as we go through the loop here, T constantly gets changed to change the actor type we're going to create the graphics for. No, not that one. Back to here, yeah. So you see the bat uses palette free, so that's palette free, and that's the bat there. And then the star uses palette 2, so that's 0, 1, 2, and so on and so forth. So this selects the graphics for them. We set the tile start and then what palette they're going to be. And then this part here, so all of them are drawn first off in place while the display is off. So you would kind of do that with all your sort of levels really. Build everything up while the display is off. We then set the horizontal and vertical positions for them, and then as these are all only going to be up and down actors, we set the bounce Y in the movement type, the animation type to loop, and then we add some more actors. So one thing to note here as well is each time through the loop we increment the actor count. That way we can just chuck in a load of actors as we go, and as long as we update this here, that should be fine. Obviously make sure you don't go over the maximum amount in the actors array. So this is just the same as the above here, except the main difference here is the movement type has changed to the horizontal one. And at the end here, this variable here is loaded with the total actors there, which is mainly used in the updating the actors code. This here moves the actors vertically if they've got that set. Checking the facing value there. If they're facing down, then check the Y position to see whether it's at the maximum screen height. If it is, then we flip the facing to facing up. Otherwise, we increment the Y position, which is passed there. Or if they're not facing down, then they must be facing up. Check to see whether they're at tile position 2 on the screen. If they are, then we flip it to facing down. So they bounce up and down on the actor move Y. And then actor move X does the same but on the X axis. You notice that in these helper functions here to move our actors, we're passing variables by reference here as pointers, and this is the move actors code here. So it uses these here to take the bytes out of the actors array first, so we can use a simple name to update, and then once we've updated the variable taken out, we then plug it back into the actors array. So this command here checks to see whether the animation type is static or not. And like I said earlier on, with regards to the tile start and then the frame ID. So the actors frame ID variable is either going to be 0 or 1. Because all of our actors only have 2 frames of animation, they pretty much all use this here. But although this is move actors on the NES version, all we're doing is we work on one actor at a time in this command here. So all of this here just moves all of these sort of actors around, but only one at a time here. And then once we've gone through the key bits here, so this command here, if the actor has actually moved, then we obviously need to redraw him in place and then erase the old position of him. And then if the actor ID gets to the end of our actors array, as in the maximum amount that we've actually created, not the maximum amount of the array, then we increment the frame. If it's 2, then we put it back to 0, and then we put the actor ID to 0. So this variable here is literally going over the array of the actors, so we only do one at a time. So once we've initialized all the actors, we sync the screen using vblank, set the tile attribute to 1 so that it the reason why I've used 1 is so the colour of the heart is actually displayed. Then turn the display back on and then show the background, and now we're good to go with the main sort of loop here. So there's the main loop. You should always update the palette or use the the load palette commands when the display is actually on, because of the way that it's kind of done in gbdk. And then we use the update timer there. When the timer lapses, we reset the timer, move the actors, and then that's it. That's all what's in here. So I think I've pretty much gone over everything I need to here. So I'll try and quickly clear things up with the attribute map, just in case there's some misunderstanding. Maybe this might help with the attribute map. So if we think of everything purely as tiles here, so the tile map is obviously represents the tile IDs on the screen, and then the attribute map is what colours the tiles will actually have. So one attribute byte is actually 4 16 by 16 blocks, so you can think of this as 1 byte. So when it corresponds to here, those 4 tiles equals one of these bit pairs. So this is actually a whole byte here. So that whole byte actually is a 32 by 32 block. So if this bottom one here was set to using the star palette, if the star moved over to this 16 by 16 block, so it would be in this part here, it would be referencing a different palette ID. So this is how you would get the attribute clash. So one thing you could do in a game is to avoid loads of the attribute sort of stuff. You could have one palette of 4 colours for the whole level, if you like. Obviously that would limit things quite a bit. That would be a quick and easy way to get around some of the attribute stuff. But as long as you kind of draw the levels while the display is off, then things should work fine for you. Won't be much of an issue. So that's it for this video. Hopefully you've learned something, and I will post up the code to it from my SourceForge page. Thanks for watching, and if you have any questions about anything I've covered here, or you think that maybe I've gone over something a bit wrong, then let me know in the comments.